Hello and welcome to our next video in CS 334, this one on how we're actually going to execute the operations we've been doing in SQL, like sorting and aggregations. Those are what we'll cover today, and then next time we'll get to joins. So I want to start out with another sort of step back and look at where we are in the course overall. So you may remember the kind of different pieces that I outlined of a database system before, where we had the disk, manager, our buffer pool manager, access methods, operator, execution, and query planning. So we've talked about disk manager and buffer pool. The access methods we have also talked about. These are our heap files or the different kind of indexes that we've talked about, different ways to access the data in our database. And so that we can check off. Operator execution we're going to talk about now, and then query planning will be after the midterm break. So just to provide some context, both for this operator execution, like what are these operators and kind of how do they fit into the bigger database system, and to set up kind of where we're headed in terms of query planning. So I want to talk about, like briefly outline, well, what is a query plan? What is it that our database system is doing when we talk about this? So let's say we have a query, select some ID from relation A, some value from relation B, from A and B, where the IDs of A and B match, and the value of B is greater than 100. So this is what a user would input in SQL, and then the database system needs to turn this into an actual set of operations with kind of a step-by-step order to them that it can actually execute. And so this is what a query plan is. And so we're going to think about them as sort of trees that we traverse from the bottom up. So we have our relations A and B, sort of the inputs to this query at the bottom, and a possible query plan might be, all right, we're going to select on B where the value is greater than 100, and here's sort of the return of our relational algebra operators. That's how we're going to kind of think about query plans, is going from this declarative language of SQL that just sort of describes the kind of data we want to some sort of concrete plan with operators that sort of are chained together. And then A, along with the result of this select on B, are joined on our ID attribute. And the final step, which I would normally put above, but I'm out of room, so I'll put it over here, is then a projection where we want A ID and B dot value. And so when we're talking about operator execution, we're talking about, all right, what data structures and algorithms are we actually going to use to do these different steps in our query plan? And so particular, today we're talking about sorting and aggregation and how we would accomplish those in a query plan. So there's sort of an easy case and a hard case when it comes to both database system operations, kind of executing operators in general, and in particular our sorting and aggregation. And this gets back to the fact that we are focused on a disk-based database management system, meaning the data is stored in kind of persistently on disk, and also we don't want to assume that the data all fits in memory. In fact, it will frequently be the case that the data does not fit in memory. So kind of easy mode is when the data does fit in memory. And so when our data is smaller than our available memory, when we can just fit all the data in memory, if we want to sort, we can use kind of any sorting algorithm we want, whatever the database decides to implement. It's frequently quicksort, and empirical tests show that this performs the fastest, though merge sort and other algorithms can achieve pretty similar performance, but we can just bring all the data into memory and apply some fast sorting algorithm. And if we're talking about aggregation, we can do that with sorting, and I'll show an example of that later on. But for example, if we wanted to group by something or do duplicate elimination, we could accomplish that by first sorting the data, and then or we could build a hash table, and this would be one of the static hash tables that we talked about, say linear probing. If the size of our data is known ahead of time, then we can kind of make the hash table the appropriate size for our data. But if we want to aggregate and our data all fits in memory, we can just construct a hash table in memory. If we were computing the sum by some sort of group, then each group is the key for each group is a key in our hash table, and the associated value is some running sum, and so we just scan through our tuples and do it that way. So today's video is going to be mainly focused on when this isn't true, when the data is bigger than memory, and when we have to design an algorithm that can handle that fact. So we're going to start with sorting and then move on to aggregation. All right, so sorting is something that we might use in an order to do an order by, for example, but we will see we might also use it to do a group by, to enforce distinct, and next time how it can be used to do joins. And when the data is bigger than what fits in memory, we need an algorithm that can incorporate using the disk to store additional information it needs. And so the algorithm that I want to talk about that is almost always the one that's used in database systems for sorting, if there's not enough space in memory, is the external merge sort. And our basic idea here is that we're going to split our data into some number of what we'll call sorted runs. So kind of a divide and conquer approach where we're going to split data into sorted runs. Run here might be kind of an unfamiliar term, and this is going to be kind of step one of our external merge sort, and then step two is going to combine our runs into a larger single file. So this splitting up data into sorted runs, this is going to be, in effect, we're going to sort small chunks of data And that's all a run is, some subset of our data that has been put in sorted order. And so we're going to sort small chunks of data and then write them to disk. So on disk, we'll have a bunch of these sorted runs, kind of subsets of our data that are sorted just within that subset. And then we're going to merge these runs together into bigger and bigger sorted chunks until we have a kind of single run that is the sorted all of our data. So what does this actually look like? So what I want to kind of put up a visualization of is a particular variation, the two-way external merge sort. And this is called two-way because we're going to kind of be merging together two things at a time. And then after we go through this two-way, we'll talk about kind of a more general version where you might be merging together k things at a time. So the way this is going to work is we have on disk we have 2 pages. So each of these kind of lumpy squares is a page, and this data isn't sorted. So I'm going to use color to illustrate kind of portions of the pages that have different values. So there's some red, and there's some blue. So these are just our kind of unsorted data files, pages sitting on disk. And then the first step is memory will be a box, disk will be a cylinder, is that in memory we're going to bring in one of the pages. And we're going to sort that page in memory. So we're going to take this page and turn it into a sorted run. So in memory, we'll have a new page that is now in sorted order, right? So we've taken this and put it into sorted order, and we're going to write it out to disk. So we still have our original pages, and now we have a new page on disk that is our sorted page. And the next step is to just do this again, bring in our other page to memory, and take it from being out of order into sorted order, where our red comes before blue, and then write it out to disk. And so now our disk has 4 pages, our 2 original ones, and our 2 sorted ones. And so this is our, this completes our step 1 here. We have kind of taken each piece of our data and produced a sorted run. So our original data is still there. And if this is say the data files for the actual table, we don't want to be actually modifying those. And so now we need to combine these into a larger single output. So what we can do is that in memory, we're going to have 2 input pages and 1 output page. and we'll bring in our two sorted runs as our input pages. So one is 2/3 red, the other is 1/3 red. And we'll just scan through these two pages and compare the keys at the kind of a particular pair of tuples, and just output the smaller one to our output page. And so we scan through these, and all the red will get output before all the blue. So we'll get a page that has all the red values here. And when this output page fills up, we then can write it out to disk and then just keep refilling it with other results as we continue scanning through our input pages. So we output this and we get the first page of our large single file that's completely sorted, and then we continue scanning through our input pages, continue comparing. We clear out or overwrite our output page. It gets filled in with the rest of the contents from our input pages. It fills up, and we output it. And so now on disk, we have a kind of all of our data in sorted order, and we did this without actually ever having the entire sorted data, these two pages, in memory at any one time. And so this was this two-step process of bringing the subsets of our data in, producing these sorted runs, putting them out on disk, and then this final merge step. So this one important property here is that this merge is going to require three buffer pages, 2 input, and 1 output. So we would not be able to do this if we had fewer than these 3 pages. So we need at least that in enough room in memory in order to do this final merge step. And in these in this first, I was bringing in 1 page at a time, but in fact, what you could do is you could bring in B pages at a time. B pages at a time, where B is the size of our buffer pool, or in any case stands for the number of pages in memory that we have available for this sorting process. So this is kind of one way of visualizing how this external merge sort is going to work. Another way, with say some actual values instead of colors, we can imagine that we have some pages to start, and each of them is just going to have 2 keys in this example, and our path, and kind of each of these kind of steps I was going through is what we'll call a pass. And so our kind of and a pass being a kind of one going through of all the data that we're working with. So this divide and conquer, where we're sorting all these separate runs, that's kind of one pass through all the data, because we kind of read in each page of the data once in order to do this first step. And then the second step will do some number of passes that it takes to merge everything together. And in this initial example, it was just a single kind of pass through the data. I just had to read through our 2 pages of data once in order to output the sorted. In this example, we'll have our pass 0, where we just take each of these individual pages and produce a sorted run. So 3, 4 stays the same, 2, 6, 4, 9, 7, 8. And so these are kind of one-page runs. And then in our pass number 1, we turn these into 2-page runs. So we'll kind of bring these in and merge them together, writing them back out to disk. And so now on disk we have a chunk of 2 pages that has data in total sorted order, and we do the same thing with these other 2 pages, produce a sorted run 4 and 7, 8 and 9, doing the same thing where we were kind of scanning through each of our input pages and then outputting the smaller of the 2 tuples, or the greater if we were sorting in descending order, into our output pages. So 4 and then 7, that page fills up, we write it out, and then 8 and then 9. And so now we have 2 2-page runs, and then we bring in these kind of 1-page. Again, we're doing kind of 3 pages at a time here, where we're bringing 2 input pages and 1 output page. So our first output page gets 2 and then 3. Then we bring in 4, 4 and 6, 4 and 7. Our next output page gets 4 and 4. Then our next output page gets 6 and 7, and then we just have 1 input page left. And so kind of it took 3 passes, kind of this initial read in all the pages to produce sorted runs, then another pass, kind of read in each page, merging them together into 2-page runs, and then third, we again had to read in each page of our data to produce the final complete sorted output. And so to put kind of a little more rigor to this are the number of passes that we're going to do, kind of the number of times we're going to read in every page of our input data. We're going to have 1 for this initial producing sorted runs, and then the number of passes it requires to merge these all together is going to be logarithmic in terms of the number of pages. So I said that we have B pages in our buffer pool. We're going to say we're going to have capital N total pages of input data. So we're going to end up seeing that kind of the expressing the cost of this external merge sort is going to be in terms of the total number of pages, and as we'll see in a bit, the number of pages B that we have available in memory. So our number of passes is going to be, I said, logarithmic in the total number of pages, and you probably remember from learning about merge sort in data structures or algorithms that when we kind of combine kind of two things at a time, we're having the number of kind of remaining chunks to be merged each time, which is going to be logarithmic. So it's actually going to be ceiling log 2 of n. Ceiling because if we have sort of don't have an even number of chunks, we still have to do a pass that reads through all of the data. So that's our number of passes, and our total cost is something we're going to measure in terms of the number of times the number of pages we have to read or write from disk. Recall in kind of our memory hierarchy, our operations on disk are way slower than any other sorts of operations in memory or cache, and so when we're thinking about the cost of something, it's really going to be dominated by these accesses to disk, and so for this, it's going to be 2n times number of passes, because each pass that we were doing, not only did we read in each page of our input data, but we also wrote out a sorted version of that page for each pass. And so each pass is reading in the page, writing out the page, and so that's kind of 2n disk IOs, disk input outputs for each pass. And so this is kind of counting disk IOs as what's going to dominate our cost. All right, so this is this kind of two-way merge that I've gone through. And I note that we require 3 buffer pages to do this. And what's a little unfortunate is that if we just kind of increase the number of pages, that doesn't actually improve this the performance of this merging step, kind of as I've described it, because if we have more pages here, we're still only writing to one output page at a time, and kind of having more pages around doesn't actually kind of save us any amount of disk I/O. We still have to kind of while we're writing this out, we're still just sort of waiting for that to finish. And the way that we can make this two-way merge sort kind of take advantage of additional pages is an optimization called double buffering. So what we want is to be able to kind of continuously be using the disk. That kind of any time we're doing some other part of our external merge sort, we want some thread in the background kind of reading or writing to disk while we're doing that, so that we can kind of get the maximum throughput, kind of the kind of maximum number of bytes read or written per second for a disk to improve performance. And so what this double buffering is that kind of while if we have, say, another page in this picture, say we have another output page, then and maybe some more input pages as well. When we fill up one output page, we can have some other thread start writing that out to disk, and meanwhile, the thread that's doing the merge just switches over to a different output page and starts outputting to that, and so we don't have to wait for the output page to be written to disk before we continue merging. And with additional input pages, we can sort of pre-fetch data off the disk, so that when we finish going through one of our input pages, we don't have to wait for a new page to be read in. It's already ready in a different page in memory, and we just switch to using that. And so double buffering is kind of the general idea that we have some buffers, some in-memory pages we're currently using, and then we have some others sort of that are on deck, that are kind of ready to be used at a moment's notice, that are available or have preloaded the data that we need. So this double buffering can let us take advantage of more memory on our two-way merge, but we can also do kind of the generalized version, as I said, where we do a k-way merge. So for our k-way external merge, what we're going to do is to use kind of all, and again we have n total pages of data, we have B buffer pages available to us. And what we'll do is that during this sort phase, so for the sort phase in the k-way merge, we're going to read B pages in. Instead of the example I showed of kind of one page at a time, sort that, write it out, we're going to read B pages in, kind of sort them all together, and then write out a sorted run of size B. So for here, we're going to read B pages at a time. And output a sorted run of size B rather than of a sorted run of a single page. And this will result in, oops, ceiling of n divided by B sorted runs. So in the two-way merge, we had n sorted runs because we were sorting one page. Here, we're sorting B pages at a time, and so we have n divided by B, kind of rounded up, that many sorted runs sitting on disk. And then the merge phase, the adjustment we're going to make there is to combine B minus 1 runs in each pass. And it's B minus 1 because we still need one page for the output. And so I have B minus 1 input pages, each taking in a page at a time from one of our n over B sorted runs. And we have one output page that we're filling up and then writing out to disk as it gets full. And so with this k-way merge, where we're sorting bigger chunks and then we're combining kind of more than two, up to B minus 1 runs at a time, are kind of our number of passes. We're still going to have one pass for our sorting step. We're still reading in each. We're still going through our input data kind of once in order to sort it, just kind of doing it in bigger chunks. So one pass from that. But the sort of savings over the two-way merge is that it's going to take fewer merge steps because we have fewer sorted runs to merge and we're merging more than one at a time. And so we're going to have log base B minus 1 because we're, by merging B minus 1 runs at a time, we're kind of reducing the number by that factor instead of by a factor of 2. And the number of runs that we have to merge is the number of sorted runs, ceiling of n over B. And it's, again, going to be the ceiling of that logarithm is the total number of passes that it's going to take. And then our total cost is, again, does not change from before. We're still doing kind of one read and one write for every page of our input data in each pass. So this k-way merge, the benefit is that it's potentially dramatically reducing the number of passes because it's combining more than two things at once. So let's put some numbers to this just to help build some intuition for how this is working. So let's say that we have a situation where we have 108 pages in our input data, and we have 5 buffer pages available. And so I want to go through each pass and talk about what's going to happen at each pass. So we have pass 0 here. We can just start plugging in the number of our values for n and b. And so if we say we have a ceiling of 108 pages, divided into five page runs. This is going to give us 22 runs, with the last run is going to be only three pages because 5 does not go evenly into 108. So this first pass is going to give us 22 runs total. And one note about this first pass is that the way that I'm defining it here, it's doing in-place sorting. So it's bringing these pages into memory and sorting them in place. So it's kind of swapping values. It's not. It doesn't require additional pages to store the sorted result. There might be situations where you can't do in-place sorting. If the pages in memory were kind of actual data that you weren't able to modify, rather than maybe copies of stuff that's on disk, then you would need you wouldn't be able to do in place, and you'd need an output page instead. But the way that we'll define it here is that this step does in place sorting. So that pass 1 gives us 22 runs, then pass 0 rather, then pass 1, kind of the first of our merges. We are going to combine we're going to combine four of our runs at a time, or b minus 1, and that's going to give us a total of 6 sorted runs that are each 6 sorted runs of 20 pages, and there'll be kind of 8 left for the last of those sorted runs. It won't be the full 20 pages. And then we'll take these 6 runs and merge them together, again, 4 at a time. And this will give us 2 runs. One of them will be 80 pages, 4 of these 20. And then the last one will be 28 pages, kind of those that are left. And then our last pass is just merging these 2 runs together, which gives us a full 108 sorted pages. And if we look at our formula for the number of passes, does it actually work out to indicate that it should be 4? Well, it's 1 plus log base 4 of 22, 108 divided by 5 rounded up, and that does actually work out to 4 if we do the math. And so this k-way external merge is going to be the standard thing that is used to do sorting in databases when the data does not fit in the available memory. So this external merge, there is an instance where we can actually do something better, potentially better than our external merge. And if we think about, do we have any data structures in our database that maybe are already sorted, and that if we want to sort our data, we might want to use one of those? Well, as we talked about last week, we have indexes like B+ trees that are specifically maintaining our data in sorted order. So could we sort using our B+ tree? And this comes down to the fact we'll only want to do this if our index is clustered. So as a sort of visual reminder of what this means, let's say we have our kind of index here, and we have kind of our pages of data kind of stored separately from the index. And at the leaf nodes of our index, we're going to have some sort of references, like a page number and an offset. This is often RID or record ID, and our leaves that refer to particular pages. And if we have a clustered index, that means that the order of the keys in the index corresponds to the order of the tuples in the data, which means that we have our leaves and all the references from the leaves to the data. That order is the same, which means that if our index is clustered and we want to get the data in sorted order, we can just go to the leftmost leaf and just read sequentially through our data in the order specified by our leaf nodes and just retrieve the data in sorted order. And our clustered index is going to make this very efficient, because it's going to tell us kind of exactly where to start reading. So this is very happy. We have a clustered index. We have nice efficient sorting. We'll have pre-sorting via our B+ tree. So what is the picture like when we have an unclustered index? Still have our data pages here. And if it's non-clustered, then our references from our leaf nodes in the index to the data are just sort of going all over the place. And so the keys in the leaf nodes are still sorted. But if we want to, say, start with the smallest key and try and read across the leaves, every single key whose value we follow to some tuple might be reading from a different page. We might kind of be jumping all over our data. And so this, not only is this not going to be helpful, it's actually going to be very bad performance-wise, because we end up doing a lot of random I/O, which we know that the disk is particularly unsuited for. And so kind of trying to use a non-clustered index is just going to make us very sad. So we don't want to do that, but if we have a clustered index, that can actually help with sorting. All right, so obviously if we have an order by in our query, sorting the data, necessary and very useful for that. But that's not all that sorting can do. So we can also use sorting, for example. We can do it with to do other things like so the other things that we might want to do would be distinct, kind of eliminate duplicates from our query. We also have queries that group by some key, and so are aggregating the data per each key and group by key in some way. So to show how sorting might be used for this, let's get up some example data here. And for this, let's say we have a relation missions that's about solar system exploration, and it has a nation who mounted the mission, the solar system body that the mission was to, a year, and a mission name. And so we have some of the tuples would be the United States mission to the moon in 1958, The first one, Pioneer 1, historic mission. The Soviet Union in 1959 slammed a probe called Luna 2 into the moon. I mean, it did some other stuff, but it did just slam right into the moon. So an exciting variation of space mission. The United States went to Venus with the Magellan mission in 1989. The USSR had the first mission in 1968 called Zond 5. The first mission to successfully orbit the moon and then return to Earth and land. So there had been other orbiters, but they had never made it back to Earth before. Zond is like a very space sounding name in English. I think it just means probe in Russian. And then maybe we also have Chinese moon mission from 2007. The Chang'e 1, first Chinese moon mission. So we have this data. We might have a query. Select. Maybe we want to actually spell distinct correctly. Maybe we want to see the nations that have mounted missions to the moon. So select distinct nation from missions where they went to the moon. So how would we use sorting to process this query? Well, there'd be several steps. So there'd be start over here. There'd be a filter step where we get just the tuples of that went to the moon. So just to not to rewrite all of this, I'll just number our rows. This is out of ink. Very sad. 1, 2, 3, 4, 5. So filter, we get rid of tuple 3 here, and we have 1, 2, 4, 5, and then we'd have we'd say remove the columns. So we throw away all the information except the ones that we need, which we've already filtered according to the body, and all we're doing is selecting distinct nations. So we can just throw away everything that isn't the nation, and we get our data, which is USA, USSR, USA, China, and then if we sort this, we get China, USA, USA, USSR, and once we have it sorted, it's quite easy to eliminate our duplicates, because that's just a one scan through the sorted data, and if we ever see a value that's the same as the one that we just saw, we can throw it away. And so once we can use a sort to make eliminating duplicates just a single scan through our data. So sorting could help us with distinct. If we could also use sorting for group by, because we could be scanning. Once we have it sorted, we can scan through our data and again kind of look, oh, is this something that we've already that we've already seen? And we'd typically use sorting as part of a group by if our output was going to be sorted. So if our query has both, has say both a group by and an order by, then using sorting for the group by is convenient because we also need to sort the data. And so if the order by and the group by are, if we're sorting by the same attribute that we're grouping by, then we sort of get a 2-for-1. But there are cases where we can actually do something more efficient than sorting to do these kind of aggregations. And so we can actually use hashing for this. So as I mentioned at the beginning, if everything is in memory, then we can just say scan through our data, and this is for queries where there's not an order. So in this query, for example, there's no ordering that's specified here, so we can kind of return there's distinct nations in any order. So using a hash table which doesn't put the data in order would be fine for this. And for distinct, right, we have a hash table. We can just kind of ignore when we would hash something that's already in our table. For group by, each group by key, that we can hash that, find the slot for it, and then if it's like a count or a sum, kind of update that aggregation, or min or max, anything like that. So the kind of where we have to try and get clever is when again our data does not fit in memory. How do we use a hashing to produce an aggregation if we can't kind of have all the data in a hash table in memory at the same time? So the algorithm that we're going to use for this is again a two-step process. And we're going to have phase 1, where we're going to partition, that is, break apart our input data into chunks that will fit in memory. So all of our data all together, too big for memory. So our first step is going to be to partition it into chunks that will fit in memory. And in particular, we need to partition it into chunks such that when we're looking at the values that are in a particular partition, in a particular chunk, those are the only ones that we need to look at in order to perform the aggregation. That if we're doing a group by and tuples that should be in the same group end up in different partitions, then we would actually need both of those partitions in memory in order to do the group by correctly. So the idea is to use a hash function, which I'll call h1. We're going to split tuples into partitions on the disk. And so how this will work is, let's say again we have this data, and this time the query that I want to run is to count the number of missions for each nation. So select nation, count from my missions table and group by nation. So I just want to compute a count for each nation. And so this first phase, this partition, is my missions table is too big for memory. And I need to split it up so that a given chunk will fit in memory. And so I'll take my data, feed it into my hash function, and this is the hash function is just going to like give me the number of or index of the partition that some particular tuple should go to. So the partition will take the data, split it up into these different chunks, and so any tuples that have the same value for nation will get the same result from the hash function, and so will go into the same partition. So like all of our USA will end up in, say, the same partition. But again, we're doing this to split into partitions on disk such that a single partition fits in memory. So we might only have a few partitions if we just need to, say, break our data into 2 or 3 or 4 pieces in order to fit it in memory. So we might have a lot of, so a single like partition might contain a lot of different values. So maybe the USSR also ends up in this same partition. So this is phase 1. We're splitting our data up so that it fits in memory, and then we have phase number 2, which I'll call rehash, which is going to take each partition one at a time, and it's going to hash, is going to go through the values in that partition and use a different hash function to construct a hash table for those values. So for each partition, use a hash function which I'll call h2, which if you remember the topic on hashing, these are going to be the same function just with a different seed. But the hash functions that will produce different values. The reason to use a different one is that we might have as in this example, we're going to have like both USA and USSR in a single partition, and so we want a different hash function that's going to be able to distinguish values that ended up in the same partition. So use a hash function h2 that is different from h1, and I'm going to use that to build the hash table for of matching tuples in that partition. So what this will look like is then we'll have our function h2, and we're going to kind of take the tuples from a particular partition, feed into that, and then this is going to construct a table where we'll have a hash table where we have the keys that we're grouping by, and then for this example query, we're computing a count. So every time we see something that we've hashed before, we just increment its count. And so this hash table that we construct from this partition now has the values of the aggregation that we need to output for our query. And kind of depending on how big the data is, we specifically know that one of these partitions fits in memory, and if needed, we could write this hash table out kind of page by page out to disk as we go through the different partitions. But by the end, we have kind of all the information about the aggregation that we're computing. And so the general idea of the entries in this hash table are of the form our group by key to a running value. So as I was saying, for whatever aggregation we're competing, if it was like the minimum, we would be saying, oh, if we haven't seen that key before, we have found the minimum for it. If we have, we check, have we found something smaller? And so this kind of hashing approach is typically going to be faster for aggregations that inquiries that don't involve the ordering, because our hash table isn't ordered, but we'll have kind of nice performance for things that don't require ordering. All right, so we've talked about kind of two different approaches to executing some of our operations, things like sorting and aggregation, and we've particularly focused on algorithms that can handle when our data is larger than memory, because when it's smaller than memory, we can kind of use an in-memory hash table, use any sorting algorithm we want, and kind of don't have to worry about this other stuff. All right, so that will do it for sorting and aggregation operators. Next time, look forward to joins, and I look forward to your questions.
Minus x minus 10.
Oh, that doesn't sound good.
8.
Yeah, I knew I shouldn't have used space mission examples.
4, 3.
Oh well.
1.
To the moon!
0.